Hello students, today we see the numerical which is related to V-belt design. First I want to read the problem statement. 3 V-belts are to be used to transmit a power from an electric motor running at 2800 rpm to a machine running at 700 rpm. The center distance between the input and output shaft is 800 mm. The shoe-groove angle is 38 degrees and the coefficient of friction between the belt and shoe is 0.5. The density of the belt material is 1100 kg per meter cube and the allowable tensile stress for the belt material is 1.75 Newton per mm square. If the cross-sectional area of each belt is 600 mm square, determine first the maximum power the belt can transmit, second the pulley pitch diameter, and third the initial tension required in each belt. Now we discuss about this problem statement. For that purpose, here we see one diagram. In this diagram, motor is shown. This motor shaft is connected to the small size pulley and here the V-belt is wound around this small size pulley and big size pulley, and as the motor rotates it transmits the same speed on small size pulley, and through this V-belt it transmits the power or rotation on big size pulley. As big size pulley is connected to the shaft which is after attached to the machine. As this pulley rotates, this same rotation is transmitted in the machine. In this way, the rotation or power is transmitted from small pulley to big size pulley or from motor to machine. Here some symbols are shown. Small n is the speed of small size pulley and small d is the diameter for small size pulley. Capital letters are used for the diameters and speed or big size pulley. That is, capital D is diameter and capital N is speed. C is the center to center distance between the two pulleys. Now we look at given data. Here number of belts used becomes 3. And the symbol used for number of belts is Z. So Z is equal to 3. Motor speed is 2800 rpm. So N is equal to 2800. Machine speed is 700 rpm, that is capital N letter. Center to center distance between input and output shaft or between the two pulleys, that is equal to C is equal to 800 mm. Shoe groove angle, as shown in this figure, this is the side view of pulley and here groove is provided, and in that groove the V-belt is mounted. This cross sectional is nothing but V-belt. The groove in which this V-belt is mounted, this groove having the total angle is 2 times beta, and which is given, that is 38 degrees. So if we want to calculate the beta, then beta is equal to 38 degree divided by 2, which is equal to 19 degrees. Coefficient of friction between belt and shoe is 0.5, which is indicated with symbol mu. Density of belt material is also given, that is 1100 kilograms per meter cube, and which is indicated with symbol rho. Allowable tensile stress for belt material is 1.75 Newton per mm square, which is indicated with sigma t. Cross sectional area of each belt is equal to A is equal to 600 mm square, means for all 3 belts cross sectional area is same, that is 600 mm square. Now first we want to calculate the maximum power the belt can transmit, so which is indicated with symbol P. And if we want to find out the total power, so we will consider number of belts also, that is P is equal to number of belts into power transmitted per belt. Here number of belts, that is Z, and power transmitted per belt, we consider P1. So P is equal to Z into P1. So for calculating the maximum power or total power, we want to calculate the power transmitted per belt, and Z is already available, that is 3. So for power transmitted per belt, we use one relation, that is P1 is equal to effective tension in tight side of belt, that is F1, minus effective tension in the slack side of the belt, that is F2, divided by 1000 into V, where V is belt speed in meters per second. So for the purpose of calculating P1, we must calculate F1, F2 and V. Then only we can calculate the P1 value. Then we have one relation, that is total tension in tight side of belt. We indicate that is FT1 is equal to effective tension in tight side of belt plus centrifugal force. And after rearranging, we get F1, that is effective tension in tight side of belt, is equal to total tension in tight side of belt, that is FT1, minus centrifugal force, that is FC. But here we want FT1 and FC both values. After calculating these two values, then only we will able to calculate F1. So for that purpose, we calculate FT1 first. And for FT1, we know the basic relation, that is stress is equal to force upon area. So in this case, stress is nothing but sigma T, which is given. Now sigma T is equal to force is, that is total tension in tight side of belt, that is FT1, and area is cross sectional area of the V belt. Rearranging this equation, we get FT1 is equal to sigma T into A. We know the value of allowable tensile stress, that is sigma T 1.75, and cross sectional area is also available, that is 600 mm square. We substitute both the values, so we get FT1 is equal to 1050 Newton. So for calculating F1, we get first value, that is FT1. Now we want the second value also, that is FC, centrifugal force. So centrifugal force is equal to total tension in tight side of belt divided by 3. We already calculate FT1, so 1050 upon 3, which is equal to 350 Newton. So here we also get second value, that is FC is equal to 350 Newton. Substituting both the values in F1 equation, so F1 is equal to FT1 minus FC, which is equal to 1050 minus 350, which is equal to 700 Newton. We get F1 value. So in calculating the equation P1, we get first value, that is F1. Now we want to calculate F2 and V, as shown in equation number 2. So for that purpose, first first we calculate the V value. So for calculating the V value, we know one equation of centrifugal force, that is centrifugal force Fc is equal to mass into V square. And how to calculate the mass? We use basic equation, mass is equal to density into volume. In this case, area is directly given, so we use the equation, that is mass is equal to rho into cross sectional area of belt into 1 divided by 1000 square. As the area is in mm square, so we convert this into meter square, so that we divide by 1000 square. Therefore m is equal to, we know the value of rho, that is 1100, substituting here, into 600 into 1 divided by 1000 square. After calculating, we get m is equal to 0.66 kilograms per meter. Then Fc is already calculated in above steps, that is Fc is equal to 350 Newton. So in equation number 8, that is Fc is equal to m into V square. If we substitute Fc and m, then we can easily find out the value of V. Therefore v square is equal to 350 upon 0.66. Therefore v square is equal to 530.30. Therefore if we take the square root, then v is equal to 23.03 meters per second. So for calculating the P1 we get two values. Now we calculate F2, that is effective tension in slack side of the belt. We know the force equation in case of belts, that is F1 upon F2 is equal to e raised to mu dash into theta, where mu dash is mu upon sine beta. We substitute in equation, so F1 upon F2 is equal to e raised to mu theta upon sine beta. So for calculating F1 upon F2, here we want mu, theta and beta values, but in given data we already have the value of coefficient of friction mu and the angle beta. So we want this angle theta. We know one relation, that is theta is equal to pi minus 2 alpha, where alpha is equal to sine inverse of, in bracket, diameter of big size pulley minus diameter of small size pulley divided by 2 into center to center distance c. So if we want to find out the angle alpha, then we must know the diameters of pulleys. Center to center distance is already given, that is c. So for calculating the diameters, we first use the belt speed relation, that is v is equal to pi into small size pulley diameter d into the speed of that pulley, that is n, divided by 60 into 1000. We already calculated the value of v, that is 23.03 meters per second. We know the speed, that is 2800 rpm. We substitute both the values, then only unknown is small d. We substitute this in equation, so 23.03 is equal to pi into d into 2800 divided by 60 into 1000. We take 60 into 1000 on left side, so 23.03 into 60 into 1000 is equal to pi into d into 2800. Therefore d is equal to 23.03 into 60 into 1000 divided by pi into 2800. Therefore d is equal to 157.09, which is nearly equal to 158 mm. This is our first answer. Also we know the ratio, speed ratio, that is speed of big size pulley, that is capital N, divided by speed of small size pulley, that is small n, is equal to diameter of small size pulley, that is small d, divided by diameter of big size pulley, that is capital D. If we observe this relation, then we know both the speeds, that is capital N and small n, and now we already calculated small d value, so only unknown is capital D. Substituting the values, therefore 700 divided by 2800 is equal to 158 divided by capital D. Then we take cross multiplication, therefore 700 into capital D is equal to 158 into 2800. Therefore D is equal to 158 into 2800 divided by 700. And now we get the answer, that is capital D is equal to 632 mm. This is our second diameter. We get both the diameters. Now we can easily find out the angle alpha. So we see the equation of alpha. Alpha is equal to sine inverse, in bracket, capital D minus small d divided by 2c. So here we substitute capital D, small d and c value, then we can get the angle alpha. So alpha is equal to sine inverse of, in bracket, capital D minus small d divided by 2 into c. Therefore alpha is equal to sine inverse of, in bracket, 632 minus 158 divided by 2 into 800. After calculating, we get alpha is equal to 19.14 degrees. But for calculating the angle theta, we must calculate this angle in radians. So if we want to convert this alpha angle into radians, we multiplied with pi upon 180. Therefore we get alpha is equal to 0.33 radians. We substitute this alpha in theta equation, so theta is equal to pi minus 2 alpha, So theta is equal to pi minus 2 into 0.33. After solving this, we get theta is equal to 2.48 radians. Now we again take the equation, that is f1 upon f2 is equal to e raised to mu theta upon sin beta. We have the values of mu, that is 0.5, theta is 2.48 radians, 2 times beta is 38, that is beta is equal to 19, and we already calculate f1 value, that is effective tension in tight side of belt, that is 700 Newton. So 700 divided by f2 is equal to e raised to in bracket 0.5 into 2.48 divided by sin 19, bracket complete. Therefore 700 upon f2 is equal to 67.83. Therefore 700 is equal to 67.83 into f2, and therefore f2 is equal to 700 divided by 67.83. We get the value of f2 now. f2 is equal to 10.32 newtons. Now we again come into the equation of power transmitted per belt, that is P1 is equal to F1 minus F2 upon 1000 into V. Now we already calculated all three values, that is F1, F2 and V. So F1 is 700 Newton, F2 is 10.32 Newton, V is 23.03 meters per second. Substituting all the values, so P1 is equal to 700 minus 10.32 divided by 1000 into 23.03. After solving, we get power transmitted per belt, that is P1 is equal to 15.88 kilowatt. Now we can easily find out the maximum power the belt can transmit, that is P is equal to number of belts, that is Z, into power transmitted per belt, that is P1. So P is equal to 3 into 15.88, and total power or maximum power the belt can transmit is equal to 47.64 kilowatts. This is our second answer. Now we also want to calculate initial tension required in each belt, that is Fi. We know the relation, that is Fi is equal to F1 plus F2 plus 2 times Fc divided by 2. We have all three values, so F1 is 700 Newton, F2 is 10.32 Newton, Fc is 350 Newton. Substituting all the values, we get Fi is equal to 700 plus 10.32 plus 2 into 350 divided by 2. Therefore, initial tension required in each belt Fi is equal to 705.16 newtons, and this is our final answer. So in this way we calculate all the three answers, that is maximum power the belt can transmit, that is P, then pulley pitch diameter, that is small d and capital D, and initial tension required in each belt, that is Fi. So here we complete this problem. Thank you.